Today we discuss the definition of hyperspaces and the relation between the hyperspaces and vector space. Let n be the linear transformation. I call this f be the linear transformation from v to f. So we call this f as linear functional. So this is the v is a vector space and f is a field. You consider a linear functional f. Suppose f is not identically zero. That means f is a non-zero linear functional. That means there exists at least one point whose image is not zero. Okay, so this is one such linear functional. So we write this is an element of v star. V is the dual space, or you can write this is an element of LVF. We have seen that in the last class, dimension of v star, that is same as the dimension of v. So if we consider v as a finite dimensional vector space, if v is a finite dimensional vector space, then we say we write the dimension of v as some n. Then what is the dimension of the null space, or what is nullity f? This is nullity. What is nullity f? Okay, so in order to get the nullity, we need to work out the elements of kernel of f. Kernel f is a set of all alpha belongs to v such that f of alpha equal to 0. Okay, so this this is always a subset of kernel is always a subset of v. So but we know that the nullity of f plus rank of f, that will be n. Okay, so in order to get the idea of this kernel f, we find the rank of f. Okay, rank of f is the dimension of range of t, the range of f here, so which is the subset of capital F. But we know that capital F is a vector space of dimension 1. Since this range of f contains one non-zero element, because we consider this v as this f as the non-zero linear functional, so the image set of f contains at least one non-zero entry, then that non-zero entry will be considered as the basis for this range of f. Then the dimension of range of f will be greater than or equal to 1, but the maximum possible dimension of capital F is 1, or the dimension is f itself. So dimension of f is equal to 1 itself, then the rank of f is equal to 1. Okay, so this will imply that this n f nullity of f is equal to n minus rank of f, that is equal to n minus 1. So the dimensionality of any nullity of this is true for any non-zero linear transformation from v to f. So nullity of any non-zero linear functional is always n minus 1, where n is the dimension of v. Okay, if v is a finite dimension, then this n minus 1 is the dimension the dimension of the kernel of f. So now we generalize, or we introduce a definition for this kind of subspaces. We know that null space is always a kernel or null space is always a we call this as null space in our terminology. This is our null space of f, that is nothing but the kernel of f. So this is always a subspace of v. Then we generalize this, or we introduce a definition for this type of this type of subspaces. That is what we call hyperspace. Okay, hyperspace is a subspace of a finite dimensional vector space whose dimension is n minus 1. In case of the finite dimensional vector space. We will introduce the definition for hyperspace for an arbitrary vector space. Okay, without mentioning the dimension of that, and we will prove that this is a very interesting statement. Uh, show that each d-dimensional subspace of an n-dimensional space is intersection of all of the null spaces of n minus d linear functionals. Okay, so there is a connection between the null spaces and the hyperspaces. In order to prove that result, we will define the definition of, we define annihilator. Annihilator is defined as the a subset. Annihilator is defined for a subset. Let us be a subset, not to be a subspace of V. This subset corresponding to the subset, we define annihilator for this subset S. That is denoted by this symbol S naught. S naught of linear functionals. This consists of all linear functionals f on V such that f alpha equals 0 for every alpha in S. Okay, so this is nothing but this is our vector space V, and we consider a subset of this. Okay, this is the subset of I call this as S. So this is the subset of V, and we consider set of all linear functionals which maps. The annihilator S naught is always a subset of V star. We collect elements from V star. So this is our F. If there is a linear functionals which maps all the elements of this vector space, this subset as 0, we call those, if we have f linear functional f which maps this to 0. Okay, 0 of f. So we call this f is an element of S naught. Okay, which is a subset of E star. So set of 4, we collect all such functionals from V to F with this property. So S naught is defined as I said, this is a subset of, this is a collection of all f from V star such that this f maps every element of S to 0, that is every alpha belongs to S. So this is the definition of this annihilator of S. So this is the definition here. S naught of a annihilator of a subset S is set of all linear functionals which satisfies this condition f of alpha equals 0 for all alpha, which that means if we choose an element f from S naught, you can say that f of something is equal to 0 for all that quantity belongs to S. So this is the definition. Now we have some remarks on that. We will consider two interesting cases. This S naught is when do we say that this S naught is V star? Okay, so if we choose S is equal to singleton set 0, if S contains only 0, then we can say that if we choose any f from V star, we can say that f of 0 equal to 0 for all f. Okay, so this is true for all f belongs to V star. That means this f is always an element of S naught in this case. So subset of V, that means every f belongs to V implies f belongs to S naught. Okay, so this every f belongs to V star implies f belongs to S naught, because S is nothing but singleton set 0. So this V coincides with S naught. Okay, so this is one V star coincides with this S naught. This is one such interesting case. Now we consider S equal to V. Okay, so in order to get f is an element of S naught, then this f should satisfy f of alpha equal to 0 for all alpha belongs to V. There is one such function which satisfies this is 0 functional. Okay, so we can say that this is a trivial subset. This contains a 0 functional. I'll write it as a bold 0. So this is always the element of, this is only the element of this S naught. So if S naught is equal to, I'll write it as equality. This is same as S naught. So we can say that this S equal to V then S naught equal to the trivial subspace. Whenever S equal to trivial subspace, then S naught is equal to V star. Okay, so these are two interesting cases. The interesting remarks on the definitions. Okay, now we will prove this theorem. If in order to define an annihilator, we need not collect the subspace. Okay? So it is enough to get the subset. Now we start theorem 16 by considering a subspace rather than a subset. Okay, let V be a finite dimensional vector space. The field F over the field F, and let W be the subspace. Here we have subspace, okay, of V. Then dimension of, then only we can think about the dimensions of R. So if W is a subspace, then dimension of W plus dimension of W naught, that is equal to dimension of V. Okay, first of all we need to verify that if W is a subspace, then this W naught, okay, S naught is always a subspace. So that is a trivial case. Even if we consider the subset S, then this is S is a subset of we then collect S naught. We have defined this S naught as this set. What is that set? S naught is equal to set of all F belongs to V star such that F of alpha equal to 0 for all alpha belongs to S. This is the definition of S naught. We can easily prove that if we choose any two element F and G from this S naught, F comma G belongs to S naught, then what is C times F plus G of alpha? That is C times F alpha plus G alpha. And if alpha is element of S, then F alpha equal to 0 using this definition. So we can say that this is equal to 0 plus 0 for all alpha belongs to S. So we have CF plus G of alpha equal to 0 for all alpha belongs to S. That consequently we can say that CF plus G belongs to S naught. So if we have S as any subset of V, then however, this S naught is a subspace. Okay, whenever you consider subset, then you can get S naught as a subspace. So this subset induces a subspace here. Okay, now here we start a subspace itself from a vector space V. Then there is no need to verify this W naught, the axioms of the subspace for this W naught. That is always a subspace. Then we can think about the dimension of W naught. Then we will prove that dimension of W plus dimension of W naught is equal to dimension of V. We prove this theorem by starting a basis of W. We have this is alpha 2, alpha 3, etc. alpha k. We have V here, and we have a subspace W here, and the subspace has a basis. Okay, so this alpha 1 etc. alpha k are elements of this subspace. This is a I'll write it as itself subset of W be a basis. We start with this basis. Then you can extend this basis to a basis of V. Since V is a finite dimensional vector space, then this can be extended alpha 1, alpha 2, etc. alpha k plus 1, etc. alpha n, or I write extend extend the basis to alpha 1, alpha 2, alpha n as a basis of V. Okay, so once you got this basis, I denote this as B, then you can construct B star, the dual base of that. Okay, so B star consists of vectors, say linear functionals f1, f2, etc., fk plus 1, etc., fn. How do you define this B star? The definition of these fi's are fi alpha j is equal to delta ij. Okay, that means f1 of alpha 1 equal to 1 and f1 of any other quantity equal to 0, Similarly, f1 of alpha, f2 of alpha 1 equal to 0, f2 of alpha 2 equal to 1. Rest of them are 0. Similarly, you can define this fi alpha j. Fi alpha j is delta ij. So this defines define the dual basis for this. Okay, we will prove that this fk plus 1 etc. fn will prove that claim. Our claim is this is a basis for w naught. Okay, I will prove that this is a basis for w naught. First of all, you have to prove that this these are elements of w naught first. Okay, so if you choose, how will you prove this is an element of w naught? If you choose an alpha belongs to w, and we'll prove that fk plus 1 of alpha is 0. Okay, fk plus 2 of alpha equals 0. That is true for every alpha belongs to w. So let alpha belongs to w. Then what is alpha? Alpha can be written as some x1 alpha 1 plus etc. xk alpha k plus xk plus 1 alpha k plus 1 plus etc. xn alpha n. Since this is an element of V, now what evaluate fk plus 1 of alpha. Fk plus 1 of alpha is fk plus 1 of this whole quantity. Then first one is x1 fk plus 1 of alpha 1 plus etc. Xk fk plus 1 of alpha k plus xk plus 1 fk plus 1 of alpha k plus 1 plus etc. From this you can say that these quantities are all 0 because fk plus 1 of alpha k plus 1 is 1, rest of them are 0. So this quantity is 0, then up to this we can say that quantities are 0. Then this will give xk plus 1, this is same as xk plus 1 itself. Okay, then using this fact, when you choose an element alpha belongs to w, we can say these quantities are all 0. Xk plus 1, xk plus 2, etc. xn are all 0 because this is a basis for alpha, this alpha 1, alpha 2, alpha 3, etc. is a basis for w's, and then any element alpha can be written as linear combination of this. So if we start this, we can say that this alpha is a linear combination of x alpha 1 plus etc. Xk alpha k, and rest of them are 0. Then what is this fk plus 1 of, then we can say that fk plus 1 of alpha equal to 0. Okay, because fk plus 1 of alpha is xk plus 1, xk plus 1 is 0 here. Then this is true for every alpha belongs to w. So we can say that for any alpha belongs to w, fk plus 1 of alpha equal to 0. Consequently, this fk plus 1 is an element of w naught. Because this maps every element of w to 0, then this fk plus 1 is an element of w naught. Similarly, you can prove this is true for fk plus 2. Fk plus 2 of alpha is xk plus 2. Then that is again 0 here for this expression. Then fk plus 2 is an element of w naught and all. So these elements fk plus 1, fk plus 2, etc. fn are all elements of w naught. And we will prove that this form a basis for this w naught. So in order to prove this is a basis, we will prove that this spans the elements of w naught, and these are linearly independent. So the linearly independence is obvious from this because B star is a dual basis. Then this is linearly independent set. Then this part is also a linearly independent set. So this is always a linearly independent set. So it remains to show that this set spans W naught. So we choose an arbitrary element from W naught, and we will prove that that arbitrary element can be expressed as a linear combination of these elements. Okay. So we start with f from this V star W naught. We will prove that this W naught is this f is a linear combination of all those fk plus 1, fk plus 2, etc. If f belongs to W naught and W naught is a subspace of V star, then this f is written as linear combination of all these elements. F1 some C1 F1 plus C2 F2 plus etc. plus CK Fk plus Ck plus 1 Fk plus 1 plus etc. plus C and Fn. So this is the general expression for this f, since this is an element of V star. And once you write this, you can prove this these coefficients. You can extract, or you can find the coefficients C1, C2, etc. From by evaluating this IF on alpha 1, alpha 2, etc. Alpha. Because if we evaluate f of alpha 1, that will be C1. F of alpha 1, that is C1, F1 of alpha 1, rest of them are 0, then this will be C1. So that we have discussed in the previous theorem. Then similarly, F of alpha I is equal to Ci. So this F can be written as F of alpha 1, F1 plus etc. F of alpha k times Fk plus etc. F of alpha 10 Fn. But we know that this quantity f of alpha 1, f of alpha 2, we will prove that these are all 0. Okay. That is because this quantity is equal to 0, because this alpha 1 is an element of W. Okay. Since alpha 1, alpha 2 all the way up to alpha k are elements of W. In fact, those are basis element. Then and this f comes from W naught. So this f maps every element of W to 0. So this f of alpha 1, this alpha 1 is an element of W, and f belongs to W naught. By definition of W naught, this term will be 0. All the way up to this f of alpha k is equal to 0, then rest of them are 0. So that is equal to f of alpha k plus 1. This alpha k plus 1 is not an element of W. Then we cannot assume that this is equal to 0. So we write the remaining term. This times fk plus 1 plus etc. C f of alpha n times fn. Okay. So this is our f. That means any f belongs to this W naught can be expressed as a linear combination of fk plus 1, fk plus 2, etc. Fn. That means this shows that the uh, set here fk plus 1, etc. Fn is a basis for W naught. That is the dimension of W naught is equal to n minus k. Okay, so this contains n minus k vectors. Okay, now from this you can write dimension of W plus dimension of W naught. If you write dimension of W as n k and dimension of W naught as n minus k, then what is the sum? Sum is nothing but n. So this is the dimension of V, and this also same as dimension of V star. Okay, so dimension of W plus dimension of W naught is equal to dimension of V. This is what we have to prove. Now we have some corollary. In that corollary, we will discuss our goal. This any W, any k-dimensional subspace can be expressed as an intersection of n minus k hyperspaces. So that we will discuss in the next class.